Hello again. I hope you can bear with me for another 10 minutes. This is another work that we have recently done. It is also related to distributed energy resources and flexibility, but this time we wanted to explore the impacts of distribution network reconfiguration. This is the content of the presentation. I will briefly explain the benefits of reconfiguration, and then we will use a highly nonlinear approach. We will use exact AC OPF for flexibility estimation. And then I have a lot of results for you to present. We analyzed the limits of aggregate flexibility, economics of flexibility provision, some operation issues, and so on. So let me first say that the benefits of network reconfiguration are very well known for a long time. As an example, I show here a legendary paper by Baron and Wu, April 1989, so more than 30 years ago. The paper is called Network Reconfiguration in Distribution Systems for Loss Reduction and Load Balancing. So benefits of reconfiguration are studied for more than 30 years, but now we have these new distributed energy resources in distribution networks. And regarding the operation of these resources and TSO-DSO coordination, the impact of network reconfiguration is yet unexplored, and this is what we want to analyze in this work. Let me this time start with a case study. We analyzed another realistic distribution network from the UK. This network has two feeders, feeder 1 and feeder 2, and you may see in the center there is a branch called NOP, which stands for the normally open point. So normally the network is operated in the radial configuration. And in the blue nodes we placed 4 flexible units with similar P and Q regulation limits, but different cost functions. So unit D located at bus 36 is the cheapest one, and other units are more expensive, which means that if we need some flexible power, we need some control actions from these units, we would rather prefer to use unit D in a flexibility market because it is a cheaper unit. Now, I don't think we should discuss all equations. We used an AC optimal power flow model in rectangular voltage coordinates. In the literature, it is called ACR OPF. And again, we introduced some binary variables corresponding to status of lines. So if some line is in service, the binary variable is 1. If we switch it off, binary variable, the status is 0. And these binary variables also translate to the P and Q power balances via power flows and injections. So this is, again, a mixed integer quadratically constrained problem. It is hard to solve. And one last thing, you may notice that we have 2 sets of objective functions and constraints. The point is that we use one objective function to find the limits of aggregated flexibility. We maximize or minimize P and Q. And we use second objective to minimize the total cost of flexibility provision for a given operating point. It is hard to solve this nonlinear mixed integer formulation. So luckily for this simple system, we can simply decompose it into 4 subproblems corresponding to 4 possible reconfigurations. And again, we implement this model in Julia and solve it with IPOP solver. Let's start with the aggregated flexibility limits. You can now see not 1, but 4 boundaries. The black line, black boundary, corresponds to normal operation radial network. So this NOP is open, and yeah, we have radial network. Then we can close the NOP and we get the same network, but now meshed operation, meshed configuration. And we have 2 more configurations corresponding to contingencies, where the entire network is supplied via feeder 1 or feeder 2. So you can see these contingency areas shown by dashed lines. An interesting thing here is, what if we want to guarantee n-1 security of flexibility services? Then we need to consider intersection of these areas. And intersection is shown by the green color. You may notice that it is significantly smaller than the overall flexible potential of the network. So it's an interesting idea that introducing n-1 security decreases flexibility services a lot. Now, we analyzed the limits of the aggregated flexibility, but then we wanted to analyze the economics of flexible power provision, and we wanted to find the optimal dispatch of flexible units. But the optimal dispatch changes for each feasible operating point in the PQ space. So to see what is going on with this network, with its flexibility, we solved the proposed OPF model for 25,000 feasible points. So we solved it 25,000 times. We discretized this feasible PQ space. One more interesting thing is that once you solve the problem 25,000 times, how even to visualize it and how to analyze it. Because if you think about this, we have 4 units. Each unit can provide P and Q control, P and Q regulations, and also each unit provides upward and downward regulation. So what we did in this manuscript, we visualized flexibility, the optimal flexible power dispatch like this. I understand this is a very complex figure. Let me try to explain what is going on. The upper row of subfigures show flexible active power management, P regulations. The bottom row, reactive power management, Q regulations. And we have 4 subfigures for P and Q because we have 4 flexible units. So we see what each flexible unit is doing in this optimized flexible unit dispatch. Finally, we have these colors, red, white, and blue, and they show the actions taken by the unit. So the red color shows that a unit consumes flexible power. Red color consumes. White color, the unit does nothing, it is inactive. And the blue color, the unit produces flexible power. And now for all of these feasible operating points, we can see what are the optimal actions. Let's first discuss what makes sense in this figure. Let me remind you that flexible unit D is the cheapest unit. And we see that it produces flexible power a lot in many feasible operating points. And this makes sense because we run this optimization, we run this flexibility market, and we find that the cheapest unit produces more flexible power than others. This makes sense. But the problems start when we move towards this direction of constrained network operation. We see that some rapid nonlinear changes happen to the operation of this unit because it is located, let's say, in a problematic part of the network with low voltages in PU, and it cannot consume more flexible power. So we see that it stops consuming flexible power, and this consumption shifts to other more expensive units. And we see many of these nonlinearities in this figure, which actually impacts the flexibility market because we cannot fully utilize the cheapest flexible unit. As you may see here, these are the subfigures for the radial network topology. We repeated the simulations for the mesh network topology. Let me repeat this animation for you. So this is radial network, mesh network, radial, meshed. What you see is that flexible unit D works much better under the meshed configuration. It is now not constrained. We don't see these nonlinearities. These nonlinearities are smoothed out and they are shifted towards more expensive units, which shows that the operation, the coordination of flexibility providers is now easier, and probably flexibility market is now more effective. Final picture, we visualize the costs for these 25,000 simulations as cost surfaces. The gray surface, radial network configuration, blue surface, meshed operation. These surfaces look similar, but if we zoom in this part where the total power consumption is increased, we see that the gray area, the gray surface, radial network operation, has some cost spikes. It grows faster, and costs under the meshed network operation, they grow slower. So we can clearly see that for some operating points, in this case, it is more efficient to operate under the mesh network configuration. Coming to the conclusions, network reconfiguration can be a very powerful tool for decreasing the cost of flexible power, but the findings presented today are very case specific. There is a need to analyze other cases. Maybe there will be some other behaviors and other network reconfigurations can be more beneficial. Finally, the proposed nonlinear model is generally hard to solve. We used a simple decomposition approach, but it is not tractable for large complex systems. So again, more research is needed here to develop tractable and scalable tools. And the final thing is we need to discuss how the information exchange between flexible units should be arranged, because to perform all of these very complex interactions, these units should have perfect coordination. If we don't have this coordination, it will be impossible even to talk about this optimal flexible unit dispatch and these complex flexibility services. That's all. Thank you for your attention.
Questions for Andrey? Hello, Andrey. I'm Akhtar from TU Eindhoven. So my question is, according to your results, when we have a radial network, we see more nonlinearity, and when we have a mesh network, we see a better consumption and production by the feasible provision units. So what is the reason for that? Is the reason could be that in mesh network we have a better voltage profile. So is that the reason, or what is the reason for that?
Yeah, thank you for your question. You're correct, better voltage profile. But as I mentioned, this is the finding only for this case. The cheapest unit is located here. So if we have NOP open, it is actually located far away from the primary substation, and the voltage is quite low. If we close NOP, the voltage profile everywhere here in this feeder goes up, and the operation of this unit is less constrained. So we demonstrate this, but again, only for this case. Other cases should be analyzed with the same methodology.
Yeah. Thank you.
Hi, I'm Rob Malhotra from Technical University Munich. I'm a bit unaware of this, the powerful algorithm you use, this rectangular relaxation. Does this guarantee exactness of solution both in mesh and radial configuration?
Yeah, thank you. There is no relaxation.
Okay.
This is exact ACOPF. You know, it can be in radial or rectangular coordinates, and both models are very well tested, but we simply applied it to a new context of this flexibility assessment. So there is no relaxation. The thing that I mentioned was decomposition, you know, like in order, we removed binary variables by decomposing into 4 possible configurations because it was easy for this case. But imagine if you have 10 lines, how many decompositions should you make? So it's hard.
Okay, thank you.
Hi, Andrey. So you're saying that you decomposed the mixed integer quadratic, right? It's a mixed integer quadratic problem, and so you solve quadratic problems separately.
Simply to continuous quadratically constrained program, yeah.
Okay. And in that case, wouldn't it make sense to also consider voltage regulation at the transformer level? What impact do you see that having on the flexibility the distribution network can provide?
It will have huge impact, huge. We saw how the results are dependent on voltage. If we add additional regulation on at the primary substation, everything will change. I think we have fixed voltage now at the primary substation to analyze this. Even this is already complex. If you introduce on-load tap changers, whatever, it will be complexified a lot. So we didn't try it.
Thank you.
Thank you.
All right, we need to move on because of time. So thank you very much, Andrey.
Thank you.
Both